Okay, in 8.1.4, we're going to be talking about revolving our areas around the y-axis or the x-axis, and using the integral in each of those cases. What do we need to do? So in 837 it says there is a solid generated by rotating the region bounded by the function y equals x squared and y equals 10. And this is going to be around the y-axis, so we end up getting this cup-like shape. We're going to examine the slice as shown in the right. What slice is formed? This is a disk. And what is the thickness of each slice? So what's a disk? It's a cylinder with a height, and so the thickness of each of them is going to be dy, because our cylinder now is going to be how much y changes. That's going to be our height. So this is a cylinder, and our height is going to be dy, which is how much y changes. The radius of each slice, then, if this is going to be y equals x squared, and we're going to be talking about the integral of y, we need to rewrite this equation in terms of y. So we're going to say, to get rid of the square root, so we're going to have x equals plus or minus the square root of y. However, this is the negative side, or this is the positive side, but we really care about this part. It's rotated around, so we're just going to have the positive square root of y. And the radius of each typical slice then is going to be that equation, which is going to be the square root of y. So this is the square root of y. So we're going to write an integral that is going to calculate the volume from 0 to 10. That's going to be how much volume is all of this shape. So we're going to say this is the integral from 0 to 10. We're going from 0 to 10 of pi r squared, and our radius is going to be the square root of y. So we're going to say square root of y squared dy. The square root of y squared is just y, so the antiderivative of y is 1/2 y squared, which means that we could take the pi out of our integral because that's just a number. So 0 to 10 of 1/2 10 squared minus 1/2 0 squared, but that doesn't matter. So that's 100 cut in half, and that's going to be 50 pi units cubed. So in this next part here, it says that Xavier doesn't like to do functions in terms of y. He likes to do the integral in terms of x instead. So he's going to take the inverse of y equals x squared and the inverse of y equals 10, and then go ahead and rotate this around the x-axis instead. And we're going to wonder if we get the same volume. So let's go ahead and do that. This time we're going to use the actual equations that were given instead of having to convert them into terms of y. We're going to leave them as is. So we're going to go from 0 to 10 once again. This time it'll be pi square root of x squared, because this equation is the square root of x. And so we had y equals x squared. The inverse of that is the square root of x. So we're going to say this is the square root of x squared dy. And that looks just like this, doesn't it? So we're going to end up having the same integral. We could say this is f of capital F of x. So this we get 1/2 x squared. So we're going to have pi from 0 to 10 of 1/2 10 squared, which gives us the same thing. So that gives us the ability to be able to evaluate and solve for the volume using horizontal slices or vertical slices. Either case, we can get the same volume. So on 38, I'm going to go ahead and draw what we need to do here. So does it matter which axis we rotate a region? Consider the region bound by y equals x squared and y equals 2x. And we have two different solids that are formed when the shaded region is rotated around the x-axis or the y-axis. So I'm going to go ahead and draw the part that is when this is rotated around our y-axis using our technology here. We end up getting a shape that is like a cup versus what if our shape was rotated around the x-axis. This one's going to be a little bit harder for me to draw. Hopefully we can get the idea of what these shapes are. Okay, so we have two different figures. Does it matter if we rotate our shaded region around the y-axis or the x-axis? Which one will produce more volume, or will it be the same? I'm going to draw a typical slice of our blue one here, so it'll look like this. We have a what's it called, a washer, versus this washer. It certainly looks like the red one will have more volume, but let's go ahead and evaluate an integral and determine how much that actually is. So we'll do the blue one first. So we have our two functions. We're going to be doing the same thing that we did above, except instead of doing disks, we're going to be doing the washer method, which means we're going to be taking a circle and we're going to be subtracting an inner circle. And we're going to find the area under the curve of the difference of each of those two areas. So we are going from 0 to 4. And we are going to be doing dy, which means we need to rewrite these equations in terms of y instead. So this is going to be x equals the square root of y, just like the previous one, and this is going to be 1/2 y equals x. So when we consider which one are we subtracting from the other, we need to think about which one is on top of the other, or which, when we evaluate from our y-axis going up. And in this case, it is going to be our x squared, or this one. So we want to take, this is going to be our outside, and we're subtracting this. So we're going to go from pi r squared, instead of r, that's going to be our square root of y. So square root of y squared. And then we can say dy, or actually let's go ahead and write it together as one integral. So minus 1/4, oh, well, let's write 1/2, pi 1/2 y squared. This entire thing, dy. We can take the pi out here, or we could just evaluate the integral as is. We're going to write this as, I'm gonna type this into our calculator here. So let's take the pi out because that would be easier. So we'll do square root of y squared is going to be y, minus 1/2 times, or 1/2 squared is going to be 1/4. 1/4 y squared dy. So I'm going to evaluate this. I'm going to show you just as a reminder how you can type this in your calculator. And then I'm going to have you guys do that on the red one. So just as a reminder of what we can type in here, we'll do pi math 9. So we're going to evaluate an integral from 0 to 4 of, we're going to change this to an x, it doesn't matter what our variable is, 1/4, I'll just say 0.25. Oops, not x divided by x squared dx. And we get 8.37. So 8.37 units cubed. So that's our volume of our blue one. Now we're going to go ahead and evaluate the red one. I want you to go ahead and pause it and try doing this one yourself, considering for the problem that we did above. So I'm going to go ahead and pause, or let you pause it right now. Okay, hopefully you had an opportunity to try. We are going to go from 0 to 2 this time because this is going to be our distance horizontally. Our outside function is going to be the line, and our equation for that is pi 2x squared minus our inside function, which is going to be x squared, so pi x squared squared dx. And we could type this entire thing into a calculator, or you can make this a little bit easier and say, take the pi out, 4x squared minus x to the fourth dx. And if you evaluate that, you'll get approximately 13.404 units cubed. And so the one rotated around our x-axis is going to have more volume. Why is that the case? Well, there could be a lot of answers for that. When we consider our radius, this red one has a much larger radius, so it's going to just have more volume. You can see that it's a bigger figure. It's rotated. It's going to be larger. Yeah. Here's going to be your assignment tonight. You only need to do A through C. You can skip D and E, I think. So just those two problems. All right. See you later on.